Mathematics, the queen of all sciences, a field of unshakable knowledge. Or is it? Almost 100 years ago, Kurt Gödel proved that the foundations of math are not as solid as we think. What does it mean, and what are the philosophical implications of this theory? Professor Adrian Moore from Oxford University is a world expert on this very subject. His latest book, Gödel Theorem, A Very Short Introduction, is a must-read for anyone interested in this mind-blowing field. He accepted my invitation to come and speak with me on his latest book. It was an honor and a delight speaking with him. Before we start the conversation, my name is Roy Yosevich, and in this channel I speak with the most interesting and intelligent people from all around the world discussing science, philosophy, artificial intelligence, and more. If you like this conversation, please consider subscribing, hit the bell button, and be part of this great community. There is lots more where that came from. And now, Professor Adrian Moore. He was a presenter of the BBC radio series, A History of the Infinite. He is the joint editor of Mind, the famous paper, the famous journal that was published by Gilbert Ryle. And he has written many books, including The Infinite, Nobel in Wisdom, Infinite and Faculty, Points of View, which he considered to be his most important book, Language, Word and Limit, and most recently, Gödel Theorem, A Very Short Introduction. So, Professor Adrian Moore, thank you so much for coming. How are you today?
I'm very well, Roy, and let me reciprocate and thank you very much for inviting me. It's extremely kind of you, and I appreciate this. This is quite an honor.
Thank you. So before the show, I told you that there is a big problem in this discussion because I have an Israeli English and you are speaking Oxfordian English. I will do my best to speak. You will do your best to understand. And let's see if we can move on. Mm-hmm. Now, am I correct? This mind was coined or was invented by Gilbert Ryle. He was the first editor.
No, that's actually not correct. He was an editor for a number of years, but it had been edited by other people before then. And in fact, one of the previous editors was a famous philosopher whose name is the same as mine, G.E. Moore. He edited the journal for a while. So, but you're quite right that Ryle edited the journal for a long while, and it is often associated with him. Yeah.
This is the same role of Principia Ethica?
Yes. Yes.
This is a big name.
Yes, G. Moore, no relation.
Okay, so I want to start. There was a very good philosopher, not a professional philosopher, named Brian McGee. He passed away recently, and he was a great advocate of philosophy for the public. I think a British version of Will Durant. And in his autobiography, he kept saying that it is almost mandatory for any modern philosopher to be equipped with modern science, quantum physics, math. And he said that in his first conversation with Bertrand Russell said the very same thing, that you cannot be a modern philosopher. And this was like, I think, 60 years ago, without knowing what modern math is all about, what modern physics is all about. And I think that this is not by chance that Russell and Wittgenstein and Karl Popper, to name just a few, were also trained in the science, not only in the humanities. Now, you wrote a book about the infinite, and our book today that we are going to discuss is going to be about Gödel Theorem. And Gödel Theorem is a math sentence. So we are going to discuss something from the theory of mathematics, but you're a professor of philosophy. Mm-hmm. So could you please elaborate on the necessity to learn or to learn science and humanities to write something about humanities?
Yes. I myself think of philosophy as a humanities discipline. But I also agree that it is increasingly important for philosophers to be engaged with the sciences and with mathematics, partly because the sciences and the mathematics are such an important part of human life. If philosophy is concerned with what it is like to be human, then at least indirectly, they're going to be concerned with sciences and with mathematics as well, because those play such a significant role in our lives. And historically, I mean, you've already mentioned some examples, but you can go back much further and find lots and lots of examples of great philosophers who have also been great mathematicians. And
Newton, Leibniz, Descartes,
exactly.
Aristotle.
Yes, indeed, that's right. And Plato, I mean, if we go all the way back to Plato, famously, I mean, this may be apocryphal, but the story goes that when he founded the School of Athens, there was an inscription above the entrance to the school which said, "Let no one enter here who is ignorant of geometry." So philosophers have always thought that maths was important. But I mean, if we think specifically about mathematics as opposed to the empirical sciences, there's no doubt that it has a lot in common with philosophy anyway, because of the way in which both of them encourage a kind of abstraction, thinking in abstract terms, thinking in terms of structures, which is as significant a component of philosophy as it is of mathematics. So the very methodology is often very similar. I mean, both of these disciplines involve sitting in your armchair and thinking very hard. So, you know, neither mathematicians nor philosophers go out and get their hands dirty in the way that other practitioners of other disciplines do. They've got a lot in common, and also there just are a lot of really, really interesting philosophical questions about mathematics. So there are always going to be philosophers that have a particular interest in the philosophy of mathematics. And as it happens, I'm one of those. I mean, I am a professional philosopher, but one of my main interests is the philosophy of mathematics. And that's part of the reason that I was interested in Gödel's theorem. It's a mathematical result, and it's proved in a rigorous mathematical way, but it's a mathematical result that raises philosophical questions, and it's a result that philosophers have always been interested in ever since Gödel established it almost a century ago.
It is like the hitchhiker guide to the galaxy, where the AI system say, okay, the meaning of the universe is 42, and then you, the philosophers, need to write about what does it mean.
Exactly.
And postulate about it, because Gödel said something profoundly important about math that we cannot have, and we are going to cover it later on. But you say, okay, but if I take Gödel theorem into the theory of knowledge, what does it mean? Okay, what are the implications of Gödel theory in the real world or the world of philosophy? And this is part of the domain of philosophy. Would you agree?
I totally agree. You've put it very well. Yeah.
Okay, so we need to go to Gödel theorem, and it's not Gödel like we say in Hebrew, and it's Gödel because he was German. Like all, I think most of the mathematicians I don't know, in the 19th century came from Germany. We had David Hilbert, and we have many others, and Kurt Gödel was one of them. And what we want to do, and I want to state it up front, we want first to explain, even to a non-mathematical audience, what is Gödel theorem? We know that he has 2 sentences. Are we going to cover just the first or the 2? What is the theorem in general? And B, which is more important in my opinion, why does it important? Okay, so with your permission, can we start with what is Gödel theorem?
Good, okay. I think it may help if we begin by thinking about geometry. Gödel's theorem is not a theorem about geometry, but I hope to explain why that's a helpful starting point. A lot of people, when they study geometry, and in particular when they study it at school, study it in an axiomatic way, what's called an axiomatic way. And this goes right the way back to a great Greek mathematician, Euclid. Exactly, there it is, Euclid's Elements. And what you find in Euclid's Elements is what's called an axiomatization. And what that means is that he starts with some absolutely fundamental principles, which are often called axioms. That's where the word axiomatization comes from. Some fundamental principles that he says he's going to take for granted. So, for example, here's an example of one of his fundamental principles. Between any 2 points on a plane, there is a straight line.
I want to show the audience that the postulates or the axioms we have just 5.
Yeah.
And they are very, very narrow. For example, what you said, and to produce a finite straight line continuously in a straight line. If you have a straight line, you can continue the straight line, and that all right angles are equal to one another. So we start with those 5 postulates. The 5th is a little bit tricky, but we start with the 5 postulates, and all 13 books of Euclid geometry rise from those 5 postulates. If we can agree on those postulates, then we can move on. And as Bertrand Russell said, when I was first introduced to geometry by my brother, he told me, I said, yes, but prove me those axioms. And he said, shut up. If you want to continue, just get the axioms.
Yeah, exactly. That's very well explained, Roy. So that's right. I mean, what you've got there are some very, very, very fundamental principles that can't themselves be proved, or that Euclid does not attempt to prove. Basically, he's saying, look, you've got to take this for granted. If you don't take these fundamental principles for granted, then you can't make any further progress. If you wanted to deny one of these principles, in effect, you would just be changing the subject. You wouldn't be talking about geometry any longer. That was the attitude. Really, really basic ideas that seem to be integral to our very understanding of space. But then, and this is the remarkable thing, on the strength of these rather meager principles, he goes on to prove more and more complicated results, more and more complicated theorems, and including the famous theorem of Pythagoras, that the square on the hypotenuse of a right-angled triangle is equal to the sum of the squares on the other two sides. And that is by no means obvious, but Euclid tries to derive it from these obvious basic principles, these starting points. Now, we could spend a long time talking about geometry, and in particular, it turns out that the situation is nowhere near as straightforward as Euclid thought it was, and there's good reason nowadays to think that space is not the way that he described it, that some of his basic principles are incorrect as a description of physical space. So, that's a big, fascinating issue.
Let me just recap. Right. Let me just please just let me just recap what you just said. Let's take, for example, the postulate or the axioms that between two dots we have only one line.
Yeah.
This holds true if our space is like a sheet of paper. Mm-hmm. But if we have a spherical space, we can think of two dots in the upper and the bottom corner, or upper and bottom centers of a sphere, and then we have infinite numbers of lines, okay? Mm-hmm. You can just draw a triangle on a balloon and just blow the balloon, and you will see that the sum of angles will be 270 degrees, not 180, okay? Yeah. So again, what Euclid said from the gods is absolutely correct, given that the axioms are correct and given the space is on a sheet of paper. You change one thing, the entire geometry changes.
Yeah.
How does it relate to Gödel?
So now we need to relate it to Gödel, as you say. So Gödel's theorem is a theorem about arithmetic, not about geometry. It's a theorem about arithmetic rather than a theorem of arithmetic. And when I use the word arithmetic, I'm using it in a fairly technical sense. What I mean by arithmetic is the study of what people call the natural numbers. And when they talk about the natural numbers, they mean 0, 1, 2, 3, etc., non-negative whole numbers. So we're not talking about fractions, and we're not talking about things like the square root of 2, and we're certainly not talking about things like the square root of -1. We're just talking about these natural numbers, the study of these natural numbers, and the operations that apply to them, like addition and multiplication. That's what I mean by arithmetic. So you might think that's a fairly modest sort of theory. But what Gödel's theorem says is that what Euclid did do or tried to do for geometry, and what can be done for geometry, cannot be done in the case of arithmetic. It is impossible to capture all the truths of arithmetic in some basic principles, fundamental principles. Supposing somebody came up with some fundamental principles and said, well, I think these capture the whole of arithmetical truth, then one or other of two things would happen. Either they will fall short, there will be some truths, some arithmetical truths that they can't prove using their principles, or they will go wrong in the other direction. They will overshoot. They'll have principles that are so strong that they can be used to prove all the arithmetical truths, but the price that you pay is that they can be used to prove some arithmetical falsehoods as well. So there's no way of sort of striking a happy medium. You're gonna either go too far in that direction or too far in that direction.
Now, this is so mind-blowing and this is so counterintuitive that I think that we need to go a little bit back. Mm-hmm. When we speak about axiom in the world of geometry, I know what we are speaking of, okay? Mm-hmm. I know that we have two lines and I know the axioms. But when you speak about axiom in the world of arithmetics, and I think that you geared toward piano arithmetic, but I don't know if this is the right time to insert it. Could you please give me an example of such an axiom? Because we don't learn arithmetic, we learn as in kindergarten. And in kindergarten, I have one candy and you have one candy. And if I take your candy, I have two candies. So why do you speak about axiom in the world, in the simple world of arithmetic?
Yeah, good. Okay, so let's think back to kindergarten. Let's think back to your first encounters with arithmetic. I mean, right at the very beginning, perhaps you are counting pieces of fruit, but eventually you'll be adding numbers and you'll be multiplying numbers. And eventually, I mean, you don't need to be that sophisticated before you're doing things like multiplying 827 by 240. And you will have been given rules that tell you how to do that. And different people are taught different rules, actually. There are different ways of doing multiplications. But if you want to multiply 827 by 240, you'll be relying on some rules, some basic principles. And in particular, in that case, 827 times 240 or whatever it was, I may have already misremembered, but 827 by 240. One of the things that you'll be doing, one of the steps that you'll have to take is you'll have to ask yourself, what is 7 times 0? Because one of these numbers ends with a 7 and one of them ends with a 0. And at some point in the calculation, the question will arise, what is 7 times 0? And one of the things that you will have been taught is that if you multiply anything by 0, you get 0. And in effect, that's an axiom. That's a basic principle about the natural numbers. Any natural number multiplied by 0 is 0. And let's think back to Bertrand Russell. I mean, if a little Bertrand Russell came along and said, yeah, but how do you know that any number multiplied by 0 is 0? We would have to give him the same answer that Russell's brother gave him, which is shut up. You know, those are
because
just because, that's right. Those are the rules, right? If you query these rules, then you're not going to get a gold star on your homework. So the truth of the matter is, I mean, you're quite right. At school, we don't learn arithmetic axiomatically in the same way that people do learn geometry axiomatically, or at least it doesn't seem as if we do. But actually, in effect, we do. We do have basic rules that we're taught. We do have basic principles that we're taught. And we use those if we're multiplying numbers or even if we're adding numbers together.
You gave a wonderful example of an axiom that we unconsciously use. And when we think about it, you say, hey, just a second, this is not straightforward. Do we have another examples in the world of arithmetic axioms that we say, this is also an axiom that we use and we cannot prove?
Yeah. So the example of any number multiplied by 0 is 0. That's pretty elementary. Something that's a bit more sophisticated although it's still a basic principle that just has to be accepted, is if you've got a property that the number 0 has, and if you can show that if ever any number has this property, then its successor must have the property as well. So if this property applies to a number n, then it also applies to n plus 1. If those two things are true, it applies to 0. And if it applies to n, it applies to n plus 1. If those two things are true, then this property will apply to all the natural numbers. Now, again, that seems fairly obvious. It's a bit more sophisticated, quite a bit more sophisticated than the principle about multiplying by 0. But it's another example of a basic principle that an arithmetician will take for granted.
And again, what you said, and this, I think that this goes back to what we call piano arithmetic. And the idea is that the way mathematicians describe the natural numbers is quite different than the normal people. Okay, we take a number n and say, okay, if n hold this property, okay, I can have n candies. I can add another, I can add 1, or the next element in the sequence is going to have the same properties, okay?
Mm-hmm.
But 0, as you said before, is a very strange number.
Mm.
So I can't put 0 into this sequence, but I cannot eliminate 0. I must have 0 if I want to multiply. So again, on the face, it seems that the foundation of arithmetics are not that clear. This is a basic, or this is a problem that Gödel wanted to solve.
Yeah, I mean, before Gödel proved his result, people were trying to do the same for arithmetic that had been done for geometry.
Principia Mathematica, for example, by Bertrand Russell.
This is a classic example. This is perhaps the classic example. Bertrand Russell, along with his former Whitehead, they wrote this enormous
unreadable tome,
totally unreadable tome, extending to 3 volumes, and their aim was to provide fundamental principles from which they could derive all arithmetical truths. And not just arithmetic, actually. I mean, they were interested in capturing other branches of mathematics as well. But in particular, if they had succeeded, they would have provided an axiomatization of arithmetic. And eventually, Gödel said, look, what they were trying to do was impossible. What they were trying to do could not be done. And in fact, Gödel's own original paper, in which he proved this theorem, mentioned this work by Russell and Whitehead in its title. It's actually part of the title of the paper, because what Gödel did was he used that as a kind of case study. He showed in particular that Russell and Whitehead had not succeeded in doing what they were trying to do, but he showed it in such a way as to rule out the very possibility of doing what they were trying to do. So it wasn't just that they themselves had slipped up, that the whole project was doomed to failure.
Okay, so the idea of the entire project of Russell and Whitehead was to establish arithmetic and math in general on solid foundations.
Yeah.
And they wanted to do it based on logic, because we know logic is true. If all humans are mortal and Socrates is a human, then Socrates is immortal, etc. But more precisely, they wanted to extract arithmetics from set theory or type theory, as Russell called it. And they say, okay, we can treat the number 2 of the, in Hebrew we say group, but group in other contexts, in English is like chavura, so it's a different thing. But we can look on all the groups of, or all the groups that have 2 elements, etc., 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 and then try to build an enormous logical building, but then something is missing. What about the group of all groups that don't include themselves in the group? Yeah. Okay, the liar paradox. And then we see the foundations are unstable. And what Gödel said almost 25 years later, he said, this is not because Russell wasn't a smart man enough. This is because this project is impossible. Yeah. You can't build solid foundations for arithmetic.
Good. Yeah. So again, what you've just said is excellent, but I think there's a crucial distinction that we have to draw. We have to draw the distinction between providing arithmetic with an axiomatic basis, and on the one hand, and on the other hand, the very specific way in which Russell and Whitehead tried to do that. Now, as it happened, I mean, everything you've said is right. As it happened, what they tried to do was they tried to provide it with a basis in set theory. And they tried to define arithmetical notions in set theoretical terms. Now, it's important to realize that that was not the problem. That wasn't the problem. I mean, that was the particular form that the project took in their case, but that wasn't where it went wrong. What Gödel showed was the problem was trying to provide an axiomatic basis at all. So suppose that Russell and Whitehead had not been interested in reducing arithmetic to set theory, or suppose they hadn't wanted their axioms to be fundamentally logical. Suppose that they were prepared to accept that arithmetical notions can only be understood in arithmetical terms. Even then, the project was doomed to failure. And that's what Gödel showed. You can't provide arithmetic with an axiomatic base at all. It's not just that you can't do so in set theoretical terms. You can't do so, full stop.
Thank you so much. Again, every other direction they would have taken would also failed. Yeah. This is what you said. Yeah. And so what is the fear? The fear is that the calculator, my calculator, tomorrow morning will produce a different result than what it produced yesterday. No, the fear is that we cannot be precisely sure 100%. And we thought that in math, we can. Math was the queen of sciences. Yeah. Not like metaphysics, the real queen of sciences.
Yeah. Again, I think I would want to draw a distinction between questions about what we can lay down as principles of proof and questions about what we can be certain of. So it may be that we can devise principles for arithmetic that are absolutely certain. Maybe. I mean, this is now philosophical, a philosophical question rather than a mathematical question. Who knows? Who knows what counts as certainty? But perhaps we can be certain that any number multiplied by 0 is 0. I mean, perhaps we can be certain of that because that's just one of our rules. I mean, that's a little bit like, maybe that's a little bit like saying that the bishop moves diagonally in chess. You know, maybe it's just a game that we've invented. Who knows? I mean, these are really, really, really deep philosophical questions, and philosophers disagree about them. But in a way, all of that is separate. We can put all of those questions to one side, whether there's certainty or not. The fact is that the principles that we lay down are not going to be strong enough to do everything that we want them to do, unless they're so strong that they include some mistakes. That's the problem. Now, let's go back to your pocket calculator. I mean, you raised a really good question. What's the worry? Is the worry that my pocket calculator will start giving the wrong results? No. There's no reason to think that your pocket calculator is going to start giving the wrong results. What is true is that your pocket calculator is incredibly limited. It does a hell of a lot, but there's also a hell of a lot that it can't do. You can get it to add numbers for you. You can get it to multiply numbers. The numbers had better not be too big. If you've got two really colossal great numbers, your pocket calculator is not going to be able to multiply them because you can't even fit them on the screen. So it's limited. And also the other thing that your pocket calculator can't do is it can't establish general truths about natural numbers, like the truth that there are infinitely many primes. It's a well-known result that there are infinitely many primes, and that has been known since Greek times, and that can be proved. But that's not something that your pocket calculator can prove.
Okay, no, but again, the pocket calculator, I think, is a good example of what is the big importance of Gödel theorem. It's not physics in a way that tomorrow morning we will have a new experiment that will deny the theory of quantum gravity or quantum mechanics. Right. This is something completely and inherently different. Mm-hmm. We know, just a second. We know that this is truth. But what you said, if our theory is complete, it is inconsistent, and in plain English, it contains error. Yeah. So I can't separate it. I'm so strong, but I can't separate truth from falsehood. This is one. And if I want to say, no, I can't accept false, I just want truth, your theory will not be complete. You need to choose between complete and inconsistent. Yeah. Inconsistent means it might be false. We don't know.
No, it's worse than that. Inconsistent means that some of it is definitely false.
Okay. Yeah. I'm sorry. And it is either complete and inconsistent, or consistent, but it's not complete. And by not complete, I mean, we can't prove it. Maybe it's true, maybe it's not true.
Yeah, I mean, suppose somebody comes up with some axioms like Euclid's axioms for geometry, except that they concern arithmetic. And let's suppose that they're consistent, that these basic principles are true. Then there will be some truths about the natural numbers that can't be proved on that basis. Now, we have to be very, very careful. We have to be very careful to emphasize on that basis. People sometimes claim that Gödel showed that there are some arithmetical truths that can't be proved, full stop. And that's not true. Gödel never proved anything of the sort. What Gödel showed is that any particular set of basic principles will have its limitations. And there will be things that you can't prove on that basis.
And again, okay, my set is limit. Okay, I will give you a bigger set, a stronger set. Yeah. Yes, but this stronger set will also has its own limitations.
That's exactly right. That's exactly right. So you start off with a limited set of axioms. You can always supplement them. You can always say, okay, so we have to add something, but there will always be limitations unless and until you sort of slip over the edge, and then you're at the point that you've got errors in your system.
Now, before we move on to the implications, and I think the implications are in the historical context of how noble a person is, what distinguishes us, can we even know something to its core? I want to take a little step backwards. Many people, I think, were introduced to Gödel theorem by Douglas Hofstadter in his Gödel-Escher-Bach. Mm-hmm. And in his Gödel-Escher-Bach, he said that one very important aspect of Gödel theorem was not just about the conclusion. It was a sentence, a theorem about natural number, a theorem of arithmetics expressed in arithmetics. And this is like where the genius came. Mm-hmm. He expressed a theory of arithmetics in arithmetics. Could you please elaborate on this point? Because I think that this is, again, mind-blowing.
Well, I'm going to disappoint you, I think, in as much as I'm inclined. I mean, sorry, let me begin again.
Don't start with "I'm going to disappoint you."
Yeah. Okay. No. Well, I say let me begin again, but I want to retain that because I am going to disappoint you. I am going to disappoint you. And the reason that I'm going to disappoint you is that although what you've just said is correct, and although the picture that Hofstadter paints is correct, in a way, it's a little bit misleading. I mean, we do best to think of Gödel's theorem as a theorem about arithmetic and not a theorem of arithmetic. And it's helpful, I think, to keep those two things separate rather than to try to run them together. Now, the thing is this, what Gödel did show as part of proving his result is that when we make certain claims about arithmetic, they can correspond to certain claims about natural numbers, certain claims in arithmetic. I mean, roughly speaking, what's going on here is that you can assign numbers to expressions and formulae that we use in arithmetic. And when we make claims about those expressions, we can sort of cash them out into corresponding claims about the natural numbers. And that's crucial to Gödel's theorem. And that's the sort of thing that Hofstadter is keen to emphasize.
And people in seminars in the math departments are totally obsessed with, but to the general public, the most important idea is not this great, cool, neat trick about how he hacked it, but what is the theory? Yes?
Yeah. Okay. And I think as far as that goes, it's it's overwhelmingly more satisfactory to keep these things separate than it is to run them together, to distinguish carefully between a theorem about arithmetic and a theorem of arithmetic. And what Gödel's theorem is a theorem about arithmetic.
Okay, so let's go to the implications, but I would want to start with the historical context. And the 19th century was a very, very arrogant century. You know, religion is nonsense. We have we are 1 century after the Enlightenment. Voltaire hated the church, and Will Durant said in Story of Civilization that 1 century after the Enlightenment, hating the church was translated into hating religion. And we dismiss the ancients, you know, the ancient Plato were just pagans, okay? And again, Whitehead said that all Western philosophy are footnotes to the work of Plato. Mm-hmm. But the 19th arrogant century just dismissed the ancient, and we thought that we are on the edge of discovering everything. And then came quantum mechanics and relativity and the Titanic and World War I. Mm-hmm. And in this context, we also have a very big bomb, Gödel theorem. So all those incidents, and Titanic is part of those. We are not that strong and smart and sophisticated as we thought we are. Could you please put Gödel theorem in the bigger context of what does it do to our humility?
Yeah, good. Okay, so Gödel's theorem has often been interpreted in exactly the way in which you've just outlined it, as, you know, yet another indication of the limitations of human inquiry, and limitations on what we can know and how much we can establish, and so on and so forth. It's often seen in that light because here's Gödel telling us that every time we try to lay down fundamental principles for arithmetic, something goes wrong. And so it does. It looks like one of these results that checks human hubris, human arrogance. But again, we have to tread very carefully. And there is a whole school of thought which Hofstadter discusses in his book, due to, in particular, John Lucas and Roger Penrose, a famous philosopher and a famous mathematician, a whole school of thought according to which we have to draw the very opposite conclusion, that actually what Gödel's theorem does is show us something about the power of the human mind, not the limitations of the human mind.
The intuition, the power of intuition.
Yeah, and the idea is that actually Gödel's theorem shows that we human beings can do something that no computer can do, for example. So if you had a computer, or, I mean, we were talking earlier about a pocket calculator, but it could be a more sophisticated version of the same thing, a computer that was programmed to prove mathematical theorems, and in particular, theorems of arithmetic. It would have to work with some basic principles and rules. It would have to work on the basis of an axiomatization. And Gödel's theorem shows that there would therefore be a problem for it. I mean, either there's stuff that it can't prove, or it contains some errors. That's what Gödel's theorem shows. But Lucas and Penrose say, what the computer can't do, we can do. The computer can't go past its own program, but we can look at the program and see how it needs to be supplemented. And admittedly, if we supplement it, the same problem will kick in again, but we always can supplement it. And according to this argument, which, by the way, I'm not endorsing, I'm outlining the argument, I'm not endorsing the argument. But according to this argument, the lesson of Gödel's theorem is a positive lesson, not a negative lesson. It's a lesson about the power of the human mind, not the limitations of the human mind.
Let me just say recap to see if I get it right, because I didn't think about it, and I think that this is a really cool idea. The idea is that if you take the side of incomplete and consistent, you said, okay, this is incomplete, but I, as a human being, have my own intuition. I don't know how. From the Latin, intuitare, I just look, I see. Okay, I got it from the God, I got it from the translator. I don't know why, but I can know things about the physical world that are absolute truth without being able to prove. By the way, this is the mere definition of intuition. You know something, you know something, but you don't know how you know it. And this might be the strength of Gödel's theorem. This might be what eventually distinguish between man and an AI system, this intuition. Okay, now this is a very positive something to draw from Gödel, but you said that you are not endorsing this argument. So yes, since you are, and in ancient Hebrew, old is smart, since you are old enough, you can say, what is your opinion on this debate?
Yes. Well, I was neither endorsing it nor rejecting it. Although...
Okay. What is your opinion?
I mean, the really cheeky answer to that question is you have to look at chapter 7 of my book. I mean, in fact, let me say that I disagree with Lucas and Penrose about this. I think...
By the way, chapter 7 is called Hilbert Program, the Human Mind and Computer.
Yeah. That's right, and in particular, this is obviously concerned with the human mind and,
yes,
and computers. Yes,
this was written before ChatGPT, I think.
Yes, so I disagree with them. I think for various reasons they may be underestimating what computers can do. And for various reasons, I think they may be overestimating what the human mind can do. So I do disagree with them. But even so, I also would want to echo what you just said about how Gödel's theorem does reveal the power of the human mind, which is what Lucas and Penrose think. I mean, to that extent, I agree with them. We can see how to supplement our incomplete axioms. And it does involve a kind of intuition. And I mean, there's a kind of intuition involved in laying down those axioms in the first place. You know, let's go back to the question that we raised earlier. Why are we so sure that any number multiplied by 0 is 0? That's a fascinating philosophical question in its own right. But something similar entitles us to supplement our incomplete axiom system in a particular way. And it is remarkable that we can do that. And that's where the really difficult philosophical questions kick in, it seems to me, because obviously there's an issue about how we do that. What is the mechanism at work here? How does the human mind work? How does the human mind tune into mathematical reality?
Now, it seems, according to what you said, mathematical reality, that if you just, write on Wikipedia philosophy of mathematics, you have many school of thoughts.
Yeah.
One of them was formalism, that math is just a set of statements. Now, if we have statements that we know to be correct, to be true, but we can't prove, maybe formalism, and in this article, they say that Gödel theory is strikes at Hilbert theorem. No, if Gödel is correct, we can say something about the meaning of math. Maybe math is something else, that you have like real, I don't know what this word means, but real mathematical entity, and you have like intuitions. And what is your take about how does the theory of Gödel correlate with different schools of thought of math?
Yeah, well, you're right. There is this school of thought, which is called formalism, whereby mathematics is just concerned with manipulating formulae. And they don't actually refer to anything independent of them. And there are a lot of people that subscribe to that view in the philosophy of mathematics, and a lot of people that are opposed to that view. One of the great controversies in the philosophy of mathematics. Now, my own view is that Gödel's theorem doesn't really help us with that debate. I don't myself think that it tells against formalism, because the formalist can always say that what their axioms are just formulae, and what they're interested in is what you can derive from those formulae. And if there are certain things that are left open by those formulae, then you have to, and you want to settle those questions, you have to add new formulae. But the formalist can still think that what you're dealing with fundamentally are formulae. I don't think the formalist need be threatened by that. And the question how you decide what to add obviously is an interesting one, and does raise some difficulties for the formalist. But it's an interesting question that raises difficulties for everybody. I mean, it's not a special problem for the formalist. So I think we have to be very, very cautious about assuming that Gödel's theorem is going to help settle any of these questions in the philosophy of mathematics.
Now, Gödel theorem was introduced in 1930s approximately, and you in the first page of your book you mentioned this date, and we are almost 100 years after. In your opinion, what has been changed in the world of math or philosophy because of this theorem? Did we stop investigating certain directions because Gödel said, no, this is a no-way zone? What do you think happened 100 years ago after?
Yeah, well, there's been a continuous philosophical discussion about the theorem of the kind that we've been engaged in, there were these arguments due to Lucas and Penrose, which have been debated and challenged, and that discussion carries on. From a purely mathematical point of view, I think, again, we probably do well to look upon Gödel's theorem as opening doors rather than closing doors. I think we can view it in a positive light rather than a negative light. It is true that what he proved was something about limitations of the axiomatic method, but actually that in itself had positive repercussions, because there were cases where you could show that you were able to do something with a certain set of axioms that you wouldn't be able to do with a weaker set of axioms. And because of Gödel's theorem, and that in itself becomes your way of recognizing that they are stronger axioms. And so there are a lot of results of that kind where you, because of Gödel's theorem, you're able to show that one particular set of axioms is more powerful than another, or stronger than another. After Gödel established his result, there were lots of examples of mathematicians applying it in that way. And also the very techniques that he used. I mean, we were talking earlier about how he translated statements about formulae into statements about natural numbers, and showed that statements about formulae could be recast as statements about natural numbers. Now, that's a matter of the techniques that he used, but those techniques have proved incredibly powerful and incredibly useful to mathematicians, and they've been applied extensively.
Let me ask you one thing. You said in an interview that one of the two philosophers that influenced you the most was Immanuel Kant.
Mm-hmm.
And Immanuel Kant spoke tremendously about the importance of math. He said that all mathematical sentences are analytically, are synthetically priori. In fact, we don't need experience to confirm them, but they tell us something new on the reality world. And there is a famous quote or a phrase by Karl Popper that he said, I don't know how he said it in English, but it was I'm a corrected Kantianian or a modified Kantianian, because I live after the revolution of quantum mechanics and the new math. Kant thought that Euclidean geometry is the only geometry possible. Mm-hmm. Kant thought that Newton or Newtonian physics is the only physics possible. Okay? In other words, if we saw something that doesn't apply to the laws of Newton, Kant would have said, you just can't see it. Something like this. And my question is, as a Kant lover, as a Kant student, would you think that Kant would change something in his theory after Gödel theorem? Let's say that Kant was introduced to Gödel theorem. Mm-hmm. What do you think?
It's a fascinating question, a really fascinating question. Kant is my own favorite philosopher. I mean, I think Kant was an extraordinary philosopher, but if we were able to resuscitate him and bring him up to date with everything that has been discovered since his time, there's a hell of a lot that would trouble him far more than Gödel's theorem for the reasons that you've given. I mean, in particular, 20th century physics would totally freak him out because, as you correctly point out, he took for granted that physical space was Euclidean. And the physicists in the 20th century told us that space was not Euclidean. So that would already have been a problem for Kant, a really serious problem for Kant. And he would have had to give up his views about geometry, at least. Now, would he have had to give up his views about arithmetic? Not yet. But now you're raising the really fascinating question whether Gödel's theorem might pose a threat to his views about arithmetic. And it is a fascinating
5
question.
plus 7 equals 12. Maybe. We don't know.
Yeah. I mean, my answer actually is the same as what I said about formalism. I think, in fact, that Gödel's theorem leaves those disputes untouched. If you're somebody like Kant who believes that arithmetic is synthetic and a priori, I think you can carry on believing that. If you're somebody who disagrees with Kant, maybe you think that arithmetic is analytic, or maybe you're sympathetic to Russell and Whitehead and you think it is logic in disguise. You may be able to carry on believing that as well. I mean, these are incredibly complicated questions.
Do you yourself, I'm sorry to interrupt, do you yourself consider the mathematical sentence, Fermat-Last theorem, as synthetic or analytic? This is a priori. This is a priori, okay? But do you think that because again, if you manipulate the sentences, so then, then many philosophers today think, no, the physical laws are synthetics, but the mathematical laws are analytic. Would you consider today, in your opinion, Pythagoras theorem is a synthetic a priori or analytic a priori?
I am uncomfortable with the distinctions, actually. I'd be one of those people that would query quite what is meant by the analytic-synthetic distinction, or for that matter, the a priori empirical distinction. And in particular, of course, that means that I would have to disagree with my great hero Kant. I mean, these were crucial distinctions for him. But I think probably the best way to think about these questions is not in those terms.
Because this is a very hard question, because I believe that God created the world with math, and what we do is discovering math, and in a way, it means that those sentences tells us something about the world. This is not like a 100 by 100 big chess game that we can decide whatever rules that we want and then play, because every time a new mathematical truth is discovered, we see how it implies to the world of physics, biology, everything, genetics. So it is very hard to say, no, this is just analytic. I think mathematical truth exists in the real world in a way that God created the world with math. So math is everywhere. Yeah. It's not just in your mind and what you think that you want to come up with. No, it intertwined in everything in the physical world.
Yeah. I mean, as it happens, lessons, I am inclined to disagree with you about that. I mean,
this is great.
That would be that. I mean, if we had much longer, that would perhaps be a point at which we would start to part company. But I think it would take us too far afield, unfortunately, now. But let me add that even if I'm right and you're wrong, which is a big if, obviously, but even if I am, you're certainly not alone in holding those views. And in particular, Gödel would have agreed with you rather than with me. Gödel's own view was very much like the view that you've just sketched. He believed that there is a mathematical reality out there that's quite independent of us, and that we're involved in discovery rather than invention. And that, we have a faculty for discovering mathematical truths, which is a bit like our five senses, which enable us to perceive the physical world. So you've got Gödel on your side, even if you haven't got me.
And we can say another thing. What is the meaning of this distinction between discovering and inventing? Yeah. Could you, like in the school of logical positivism, I'm sorry, what does it mean? Okay, so give me one example that if you invent math, it goes like this, and if you discover math, it goes like this. And it is very hard to find something in the reality, in the real world, that we say, okay, this incident will separate between invention and discovery school.
Yeah,
don't have.
I agree. I mean, I mean, they're just metaphors, aren't they? And it's very hard to explain what the difference comes to. I mean, I think the best way of teasing out the disagreement here, if there is a disagreement, would be by thinking about how we would react if we came across aliens,
yes,
who did mathematics differently. So suppose these little green men land and they're sophisticated enough that we can start to communicate with them. Either we learn their language or they're able to learn English, let's say. And we find that we have a lot in common with them, but we also find that there are a lot of differences. And in particular, it turns out that their mathematics is strikingly different from ours, and perhaps even looks incompatible with ours.
But until such alien comes, we can see debate. But as my friend said once, the best proof that super intelligent creatures exist in the universe is that they choose not to go here, not to come visit. Okay, this is what. Now, Adrian, first, thank you so much for your time. It was, I don't have another adjective beside mind-blowing, but it was really expanding the mind. In your interview, you said something that I highlight because I love so much those parts of the interview. And it was, what is or what was your writing routine? Because you write many, many books and you are editor of a philosophical journal. And you said it is, just as has always been, pretty rigid. In fact, during a lengthy period of sustained writing, my routine is not unlike that of a typical 9-to-5 job. I'm liable to start at the same time each day, early to mid-morning, and to finish at the same time each day, late afternoon to early evening, with a break for lunch. My graduate friends often used to tease me for putting my pen down at precisely 6 p.m. because you are a Kant student, yes?
Yes.
No matter what stage. Well, I was in my writing, even if I was in the middle of a sentence. Could you please say or give some tips to people who want to write more? Might be academic papers or new books about your writing beside what I just read?
Well, once again, I'm sorry to say that I'm going to disappoint you, because students often ask me a similar question. You know, what advice do I give them about writing routines and such like? But I don't like to give advice, because I think so much of this is personal. I mean, as it happens, I am a creature of habit, and I couldn't really work in any other way. But I know that that's a matter of temperament, and other people work very, very differently, and it can be just as effective. So I don't want to be prescriptive about this. I think what you've got to try to do, anybody that's interested in doing sustained academic work, what you've got to try to do is to find your own way of doing it, the way that is most comfortable for you as an individual.
Adrian, I don't know. You are talking, and in my head, I'm just planning our next conversation, maybe on the infinity, or 5 or points of view, your most important book. I want to thank you again so much. It was a wonderful conversation. Thank you for your time.
Thank you very much. I really appreciate it, and I would be only too pleased to have another conversation with you at some time. That would be great.
Thank you, Adrian. Bye-bye.
Goodbye.